I will move to English because one of the speakers is not French speaking, and we had so far the interaction in English. And so first of all, thanks for inviting me for chairing this session. When I've been invited, I was thinking it was a little bit out of scope because I'm more on the software side. So I'm Gianluca Bontempi. I'm professor not so far from here in ULB, and I founded the machine learning group in ULB more or less 20 years ago. But when I realized the topic, I remember that in my early career, I've been also working on the outdoor aspects. I've been researcher, postdoc in Philips Research in Imec. And so at the time, one important keyword, which is still a major keyword today, is the keywords of co-design. And so we were discussing about the large dimension of the AI problem. And indeed, if we add hardware to this dimension, we realize that this space of design is still larger. And so we will have today a very important representative of this interaction between hardware and software. In order to introduce them, I asked them to prepare some slides. And so I hope that now I'm able to, yeah. So I will ask each of them to introduce briefly themselves on the basis of the slides they prepared. So François, Terrier, please have the floor.
Thank you. So I will present shortly the CEA activity in this scope. So we have several offices and centers of CEA in all the France with two main centers. You can go to the first one. It's not a problem. Two main centers, one in Saclay, one other in Grenoble, tackling both software and hardware aspects of AI. Okay, next. And all these activities can be seen with two visions. One, science for AI. So we work on the subject of the AI itself with three parts: algorithms and frugality, trust of AI, and energy efficiency and microelectronics for AI. And the other visions is the use of AI for science and society, so for developing applications, both for the needs of the CEA research, but also to answer and provide new applications to the industry and partner of the society. We can go to the last one in order to finish. And what is important and what I want to underline today is that there is a continuum of challenge going from the data to the implementations. And what is really important is to be able to manage and to deal with all the aspects of these continuums. So going from data, developing algorithms, tools, and architecture in order to implement at the end as best as possible the AI applications. This concerns data engineering, algorithm engineering, trust engineering, deployment and optimization. So there we are closer to the hardware, and obviously architecture component and technology definitions. Thank you.
Thanks a lot for your introduction. So we'll move to Professor Latré, from Research Director in Imec.
Yeah, good morning, everyone. I'm glad I'm not the only software guy in the room today, but I work at Imec, which is, of course, a more hardware-oriented organization. So I'm Steven Latré. I'm a professor at the University of Antwerp on the one hand, and also part of the research center of Imec. Right now, at least for the next 2 weeks, I'm leading a research group on connectivity and machine learning. But in 2 weeks from now, I'm going to start full-time at Imec, leading the AI activities there. This is a new role at Imec, and it actually shows the emphasis that Imec, as a semiconductor research organization, wants to put also on AI in the future, which was already the case in the past as well. Next slide, please. So if you look at what we do at Imec, we of course leverage upon our existing semiconductor and system technology we have already. So aspects such as sensor technology, CORSE, CMOS, flexible technologies are the core of what we do at Imec. But on the top, we apply this to several specific verticals. We have several solutions for health, several solutions for automotive, and so on. And we believe strongly that AI is actually that connecting factor which enables the gap between our core technology and the applications. And for us, this means doing AI research, hardware-software co-design, both at the distributed edge of it all, so really very small devices, very small energy footprints, but also focus a lot on large-scale compute for AI. So how can we build novel AI chips combined with algorithms that are able to do high-performance computing as well? So if you look at the type of realizations we have, we've built in the past several AI chips that can really work at the edge, supporting traditional deep neural networks such as convolutional neural networks, but also supporting more second generation neural networks such as spiking neural networks. But we also develop specific sensors, which then typically generate a lot of data as well, which is key for our AI. So, for example, the neural pixel is a specific neural probe, which generates at a very high frequency a lot of data, and we have a 140 gigahertz radar as well for automotive. Why am I explaining these specific examples? This is not AI. But of course, this needs a lot of AI, and that's to François' comment as well. It's really the combination of hardware, software, which comes together where you can build an end-to-end approach. And I have a very small video of something we showed. I'm not sure if that will work or not.
Okay.
We'll see. Apparently not, but it was a very nice end-to-end example of how we combine our Imec radar with an AI solution. This was a gesture recognition allowing you to play Space Invaders using a spiking neural network gesture recognition system, just to show you that end-to-end AI hardware software is really very important as well.
Okay, thank you, Steven. So we move to Professor Fraboulet, Scientific Director of the French Ministry of Research.
Hello, everybody. So I'm very pleased to be here. Maybe I will paraphrase a lot Renaud Vedel, who spoke first, and is a coordinator and a brilliant coordinator of AI in France, as he explained. So my current position is at the Ministry of Research and Innovation. So we are basically dealing on a bunch of strategies in France, from digital software to digital hardware. And I also very much want to emphasize on the interface between the two. I'm very happy to be on this round table. So basically you understood in France we have, maybe we can move on to next slide. I will try to be very short. You understand we have a very structured ecosystem on AI with huge project, as we said, with Renault, with Isabelle Erlin on research. So on the industry side, we have a lot of challenges going on. On the research side, we have a pretty well structured now system with at least 4 dedicated institutes, plus extras like data IR and so forth. I was wrong about the number of chairs. I understand Renaud gave a little more than I do. But anyway, it's a huge, let's say, huge work. And we have a dedicated computing infrastructure everybody is aware of, which also is important, and we try to increase it. It is a French structure, but it is also open to Europe and international. Basically, as was said earlier by Renaud, by Nathanael, let's say the scale is not French, is at least Europe. So we are very happy to be here to discuss how we can organize all together. So I can comment on the fact that we have a lot of discussions with German people so far, with Japan, and we are very pleased to say we will go further, obviously, especially on the interface hardware, software with Japanese people. We are not so bad on the system. We could comment on Singapore, on other, but whatever, we are very pleased to carry on with other European colleagues, because, as I said, the scale is at this level, at least, I would say. At the European level, there are a lot of, let's say, synergies to be found. I will not comment further. And we already said that at the international level with France and Canada and other, many others, we have the GPI, which is also very much dealt by Renaud, by Isabelle, etc. So open, and also the last... I may have the last slide. We also would like to go from fundamentals to application to get the full spectrum of let's say, the innovation and the value chain, let's say. So very briefly, I wouldn't want to comment on overseas and USA examples, but everybody has understood that Tesla, for instance, is very, very proactive in system, both on the supercomputing side, dealing with their own chip now to make the learning, and at the real-time embedded IA with also their own chip now. We hope that in France and in Europe we will be able to do the same. You probably, I think you mentioned the works with Valeo, with Safran, and also we may comment about the fact that STMicro is quite well involved in the Mobileye with the Intel. But I strongly believe that there are a lot of other links that can be done with the industry, in the European industry, for instance, with automotive, with much more delegation, and also in aeronautics. So this is what we have to discuss right now. Thank you very much.
Thank you. So now we move to Fabrice Rastello, Research Director at Inria.
Hello, hello everybody. So I'm a research director at Inria, which doesn't mean I'm at the direction of Inria. So still I will do a short detour to try to explain a little bit what Inria, and speak a little bit more about research in France. So when I think about computer science in France in terms of academic research, I think of obviously CEA, but also the university, CNRS, and Inria. And so I am at the head of research group at Inria, which means that basically it regroups several researchers from those different institutes. So that's how it works. So my current interests are around, obviously, there's artificial intelligence in that. So yeah, at Inria, if I think about all the teams that work in AI, there are obviously people who use AI as a tool, people who work on AI itself, and people who work on optimizing the AI. And that's optimizing the AI is basically what is the main purpose of the team I'm leading. But as everybody, we are also using AI, and we are using AI for compiler. We are using AI for teaching, programming, and for other stuff. So let's. So I just want to last slide to clarify what I mean by optimizing, and so basically you take a program, and I mean this program can be a workload like just a single layer of a neural network, and you need to have in mind that there are many combinatorial number of possible ways to express as is to a binary that will do exactly what is expressed in the original program. I'm not talking about all the transformations we may do, algebraic transformations. It's just doing exactly the same. This is, if I just take an example of a 2D convolution, and just consider the very simple architecture and all the reasonable binaries that I would think about, there are like 10 to the power of 20 possible ones, and the compiler needs to choose one, the one that has the best performance. And so I have just a short quiz to finish with. So basically, a lot of manufacturers and people who sell chips or even services like clouds, they valorize it by making frameworks and libraries. In those libraries, they optimize specific operators. So there are engineers that spend years in optimizing this. And so that's what I call optimized library. So you take a 2D convolution binary, and the question is, what do you think is faster? So the generic compiler that takes a generic conv2D, the optimized library, or a domain-specific compiler. And more importantly, how much faster one is compared to another one. So I'll let you just think about a few seconds. And so I would have said the manufacturer optimized library. And it turns out, actually, they're in order. Generic compiler is the worst. Then the manufacturer optimized library is better. And then the domain-specific compiler is even better. And the order of magnitude in a simple CPU superscalar architecture is, I tell you what, 1,000. Okay. So it's just 1,000 faster. And okay, what it means is that the original version goes very slow. Okay. And the domain-specific compiler, there's still a lot to gain. So just the conclusion of my slides.
Okay. So thank you. So a lot of food for reflection, for thoughts now. So, but since this is a meeting between Belgium and France, so I think I would start more probably from the political perspective of collaboration between Belgium and France. So there has been recently signed a strategic platform of collaboration between two major entities in Belgium and France, CEA and Imec. About collaboration on semiconductors for AI. So this is typically what people read in the news. I wanted to know more about what's happening in practice. So this agreement has been signed several years ago. So I would like to have news about that, what's happening, and more from the perspective of the actual people implementing this kind of agreement. What is your perspective, your opinion? In general, if you can comment in general about the CHIPS Act, also all the initiatives, both from the researcher perspective, please.
Okay, I will start, and I hope you can complete a lot. So in fact, it's a long story. Yeah. So it's the agreement is not very some years has been made some years ago. It's running, and what it's clear is that CA, in particular, the microelectronic parts of CA called the LETI, you mentioned previously. So has the volunteer to have a convergent strategy on microelectronics, and it's why there is some agreement signed with Imec in order to synchronize our roadmap, to share the view, and to be stronger together in order to build the solutions. And all the examples you mentioned previously, I could present them, but I just choose another way to present our activity. So there is real convergence on the technology, on the activities. And what is very important for this today for me is that there is also a common interest on and conscience and ambitions on providing microelectronic solutions for AI. Because there is a real challenge on the technology to support AI, performant AI, low consumption AI for very small embedded system or very large computer, but with lower energy consumptions, more efficiency. And on these actions, for example, we are together proposing some European testing experiment facilities, the TEF, with a common projects that I hope is under evaluations, but I think it's a very nice proposal. It's one example. We have some other collaborations in European projects supported by the Digital Europe framework, for example, on these subjects. And we are now building strategic projects on the deployment of AI. So it's more to deploy algorithms coming from deep learning to embedded systems, different hardware systems. It's also a project with a European part where we will go together with Imec and with the national parts, very important and strategic. Perhaps Renaud can comment too, because it's in the scope of the national coordinations. And the idea is to have an open source platforms that will ease the deployment of deep learning on various hardware solutions, including very efficient and performant solutions.
So I think François already told most of it, but indeed most of the collaborations are on the side of neuromorphic hardware as well, and then the algorithmic side. Maybe looking at the future, I think there's a lot more potential as well to go forward with that. I think the EU Chips Act can be a catalyst for that on the one hand. We also saw that in the last few years, every country, as already mentioned, developed their own coalition, their own strategies, and I think now it's the time to come together again and to have further collaborations and further conversations on how these different coalitions can come together. I think everybody has its own expertise now, which helps in the conversations and the collaborations as well, and I'm sure that we will see more of that in the very near future as well.
Okay. Please.
Just one compliment is on all these actions. We have a strong, close actions with between CEA and Imec, but we also associate other European partners. And in most of them, we have collaboration with Fraunhofer, and sometimes with some other country in Austria, Italy, and other. It's not a closed cooperation. It's an open one.
Okay. It was mentioned before, so Intel will be another major actor appearing also in France. Now, do you expect that he will be involved in this kind of strategic collaboration? So, probably it's a delicate question.
I hope that the French government will not allow they will be out of this kind of cooperations, because if they have 1,000 of researchers in AI in Saclay Plateau, it would make no sense that they have no collaborations with the academic and very rich academic ecosystems of the plateau, and probably at the European level, because it's easy to go from the plateau de Saclay to Brussels and other European countries.
Please.
This is a very delicate question. I'm just talking from my own, not representing the French government on this, but I can tell that we try to discuss as much as possible with the Intel guys, because, as you understood, their research center should be, let's say, based firstly in Paris-Saclay, but it doesn't mean they will not work with the whole European research community, of course. And my strong conviction is that if we want to get out from the top, as we say, with this situation, we have to put in front of Intel our best people, our best efforts, and to make sure that we go further with them, for instance, on training for circuit conception, training for architecture or specific circuits, etc. I'm pretty sure, working with them, nobody can tell that Intel is not still a very huge leader on this field. We will learn a lot. And we have to work with them to try to make sure we take something out of this situation. This is my strong conviction.
Okay, thank you. So now we move more to a discussion about the education part. So as I told you, I'm more from the software perspective. And nowadays AI is everywhere, and there is somewhat delusion, mainly from sometimes also from young people, that to become an AI is to learn some Python library for doing TensorFlow. It's all about that, and then you are an AI data scientist. I would like that you really mention to these people, to those researchers, what they are missing in the vision of what it means to have an AI application. So I would like that each of you try to explain, if I'm just this naive scientists who just care for the software, the other side of the moon, or what is missing? So please.
Yeah, so, so the first point is indeed when I learned computer science, I mean basically we're learning algorithmics and arithmetic complexity. That's what we were learning, and we were already missing a very big part of the story, which is basically what about all the communications, the I/O. Okay, that's what I can't remember. Someone said before. Most of the energy doesn't come from the number of computation we are doing, but from the number of data movements we are doing. And we definitely need to, when we are programming, to be aware of why this version of algorithm is going to be good or not for the architecture. Is it going to be, just basically be hardware aware when we are programming is something that we need to teach, and it looks to me that most of the, I mean, an important part of the teaching right now is about kind of cookbook, right? And so we are already missing the algorithmic part. So yeah, we need to put a lot of efforts in this, because as I said before, there is a huge, really several orders of magnitudes to gain in terms of energy. And the example I took during my introduction is a super simple one. It's too simple. And reality is way more complex.
Maybe I will have a very off-the-track comment about that. It happens that this morning with a colleague we were talking about autonomous vehicles, of course, and autonomous planes. It happens also my son is pilot, and I am interested in this field for more than 10 years. Mm-hmm. And I think that beyond everything which was said, that you don't make IA only on the technical side, you have to see the economic side, the juridical side. You also have to see the applicative environment. So when a pilot will have, let's say, added autonomous system to reduce or to augment his delegation, what we have to understand is obviously the system will be smarter, more intelligent, artificially intelligent, but it will be also more complex. And what is the work of a pilot is to deal degraded situations. And the more the system is complex, the simpler the usual day-to-day work is, but the more complex the degraded situation is, because the system is more complex. So my son says to me, okay, your system, you want to make it automatic, okay, but when it doesn't go well, it is worse for me. I have to understand what's going wrong. And so what I tend to say with this very personal example, let's say, is that we have to take the full picture of the system, the application, let's say the work and the professionals that will deal with it. It is true in a plane, it will be true in an autonomous system, let's say a driving, autonomous driving car, or not completely autonomous. It is also true when, let's say, a medics will have to deal with a semi-automatic diagnosis or whatever. And we have to go deeper in the professional environment where we will bring this system. I would say it is part of the deal. It is not only, as you said, being a software engineer and dealing with, I don't remember what you said, but whatever, system or code.
Thank you.
Okay, it's a complex question, so I will give a more personal answer related to some process I made in AI. In fact, my position is just to explain that AI doesn't exist. It's just software. It's something that is artificial. It's sure. Intelligent? No. So if the student understands this, after we can discuss. We can say, okay, it is why you need to understand what you are doing. And if it seems magic or free, it means that you have to pay something somewhere. And probably you don't know what you pay, and it's probably expensive. So you use a lot of data, it costs a lot of energy. It's immediate, very easy to build. It means that you don't have trust. You don't know what you have built. And it's really the way I would like that the young engineer in AI considers AI is to consider that it's so it's serious as much as classical software. So we have to take care about the quality of the process, the quality of the data, the quality of the development of the testing, and so on. And if they agree to these questions, perhaps we can use AI to have very, very nice, exciting, efficient applications that will build a better world for the human. Else.
Okay. Yeah, being a software guy at a hardware research organization, I'm a strong advocate, of course, of saying we need to look at this together. And there are a number of reasons for that. I think on the one hand, often the word is being said is that AI is going to be the electricity invention, at least in the future. So that means it will be everywhere. So it will not only be in big data centers, as we have a lot of examples of right now, but it's going to be really everywhere, from your small earbuds, headphones, to in the car, in a plane. And you see that with a lot of innovations right now, a lot of chips coming up right now specifically for AI. So it's going to be important to always look at these parts together. If you do not do that, you will never be able to optimize, as you said, as well. The second reason is that I also think that it's going to be necessary to look at this together if you want to make sure that AI will be continuing to make the improvements that it is right now, because we'll probably touch upon energy consumption and so on later on as well. But if we are not looking at the combination of hardware, software, there will be a roadblock in the very, very near future already up ahead, where the model complexity of artificial intelligence systems is becoming so high that it surpasses of what we can do with hardware, with current hardware as well. And then we're ending up, or there's at least a risk, that we're ending up in another AI winter with all of this. So you need to look at it together for sure. And I think it's something that is not happening in a decent way enough. I think it's still two, three separate worlds that are researching this together. There are examples, of course, but it's not enough. And the last reason why, especially for European researchers or students, I would definitely say this is that there is a very strong research expertise on hardware, on semiconducting technologies in Europe. This is for us still a very important USP. So yeah, why not look at that combination then, because it will drive a lot of potential innovation in the future as well.
Thank you. So we can do interactively. I don't know if in the audience there are some questions for the experts. In case you don't hesitate just to raise your hand. So, okay, you can always ask. Please, Nathan.
What are the current collaboration between you both,
Yeah, so it's a bit about what François already mentioned. So the most important collaborations that we have right now, well, there are plenty of them. At the AI side, it's mainly on the edge devices, so edge AI neuromorphic next generation devices. But of course, the collaboration between CI and Imec goes much further in that.
Thank you. About the discussion we were having before, so the role of software and hardware, I have the feeling that sometimes also the way how the algorithms are assessed also in publication. So people, at least from my domain, take care much more about the accuracy, about the precision of the algorithm. It tends to forget all the rest, the energy, the computing time. And also if you look, for instance, a very common competition you have on the net, like Kaggle, so people just look at forecasting competition, people just look at accuracy. Don't you think that integrating additional cost functions also in the assessment of the algorithm of the publication related to energy would help opening somewhat the community and making more concrete and more realistic also the kind of development of algorithm? Because I mean, if you need to spend 10 times more energy to gain 0.1% of accuracy, I mean, people should ask themselves it's worthwhile. So don't you think it's also a matter of how we as a community, or at least the machine learning, the AI community is assessing algorithm? Wouldn't be interesting indeed to stress that this energy component or this computation time should always appear somewhat in the benchmarking or in the results? Probably your community is doing more than mine, but I would like to have your feeling on that. Please.
Actually, I don't know. I mean, you already said, I think it's important.
Yeah.
Obviously, in our community, we are looking at that. I mean, that's an objective. But maybe the question, I mean, this is what I was saying originally. Maybe we need to make more efforts so that people who are developing applications, I mean, a lot of them are already trying to reduce the like, you know, you can teach and make a smaller network. You don't do quantization. I mean, there are lots of stuff people are doing, but so it's already the case. What I was saying before is that basically what is missing is really that those people are not aware that it's not because they are reducing the number of computation that they do have an impact on the energy, that they do an impact on the performance. I don't know if maybe it's too expert, maybe it's too difficult, but we need somehow to make the bridge between the communities. It's really important.
I may add a very trivial remark about the quiz that Fabrice explained to us. And the 1,000 times, this is what you have to remember. You can gain 1,000 times of, let's say, efficiency. It can be energy efficiency, as you said. I compute less, I consume less. But there is also something to take into account, which is not easy at all when we are talking about specific, and we all want to make specific chips more optimized, etc. There is a compromise between, let's say, versatility and optimization. And what you gain having 1,000 times better is you are extremely specific. So on the chip side, on the conception side, it is extremely expensive. It is, and you lose a lot of flexibility, let's say the flexibility of the processor. Everybody knows the difference between a processor and an ASIC. Of course, when you do an ASIC, it is relevant when you can produce it in huge quantities and when you have a very specific problem. When you don't know exactly what you want to do, maybe you tend to make more microcontrollers or computers, etc., etc. And so there is a compromise. And so the compromise of optimization is the same for, let's say, energy reduction, etc. It's the same.
Yeah, I think what the pure software AI researchers are often ignoring is that we're hitting very fast that computational bottleneck. If you look at how the current AI models are evolving, they're more or less doubling every 6 months. If you compare that to Moore's law, which doubles every 2 years with a bit of luck, it's very soon that we will end up in a situation that we're not going to be able to run the most complex models that we can dream of anymore on big hardware, even on big hardware. And that has a computational aspect, but that has definitely also a sustainable energy aspect as well. If you look at GPT-3, the current carbon emission necessary for actually training GPT-3 is equivalent of driving with your car to the moon and back. And it has a result that right now we're only able to train and build those models really in very large data centers. So we will need to get to not only 1,000 factor reduction, but probably to 1,000,000 factor reduction. And you can only do that if you do this across the board. If you do that on hardware level, you try to aim for 100,000. At compiler level, you try to aim for 101,000. And at software level, you do that as well. And what I'm often missing is that from a software AI perspective is that people are often building and proposing the perfect neural network architecture. But if you then look at the implementation of it, there might have been a more suboptimal choice that you could have taken from a software perspective. But it would, if you could combine it all together, it would be much more optimal. And that's what I'm really missing right now in a lot of fields.
Okay.
Yes, just one comment. I think the point you underline is very important, because at this moment, my personal feeling is that the research community in AI is very few concerned by frugality. Frugality both in energy, but also in data, because if you reduce the amount of data you need, and if you reduce the computation to build the models, it's very, very important. And it's a subject that emerged, but now, this year or last year, but it's quite recent. And so any actions we could do to push to consider these aspects, for example, proposing to the competitions to have these indicators on energy, amount of data, amount of computations, any indicator we can have would be a good thing. And if someone has the power to push these indicators, do it, because it will help everybody. So I think it's quite important to really to push this concept. Trust is understood now, because we talk about trust from 5 years ago, I would say. Frugality is more recent. But
and about frugality, don't you think that there is a bias in the community when you are talking about AI and hardware? People are thinking about deep learning, which means very complex architecture, which means very complex model, and from a pure statistical perspective, deep learning tends to be excessive on a lot of perspective in terms of parameters. And so I was wondering if there are efforts also in making make smart implementation also of models which are not so big and large as deep learning. So, in statistics, there are a lot of useful models which are much more frugal than deep learning. Why I think also for question of fashion, people tend to also. And so if you look for instance, for a platform for IoT, you have sometimes the library for deep learning. You don't have yet a library for much simpler models. So, seems a bit odd to start from the beginning with the most complex approach. So, what is your opinion?
Yes, so I think it's also a good point. And I have a seminar yesterday with internally at CEA with people who are working on nuclear instrumentation, so equipment to detect some radiations and some things. And they propose some algorithms AI-based with deep learning and so on. And our AI research teams were there and said, okay, but why do you use deep learning? You can have perfect and perhaps better performance with a very classical clustering algorithms with a low cost and so on. They said, we don't know. we was aware that AI is deep learning, but not also something else. And I think the lesson there is that there is no presentations and clear visions on the different technology and of their roles. And I was impressed because I discussed with the researchers of these teams at CEA, the AI teams, and they have built a table where they said, okay, SVM, random forest, and so on. They took all the technologies they know, deep learning, obviously, and they, on the line, they put some type of applications, and they put a comment across. And internally, when someone comes with an application, they say, okay, where it goes. And after they discuss, they analyze more deeply. And I think we need these visions. And we need to share these visions in order really to push AI on the good technologies and not only on the most advanced, that is very nice and very, very best, but
not necessarily from a statistical
sometimes
perspective, the most
to
complex
yes.
is the most accurate as well.
After there is some other tracks that comes, but it's more for research and long-term time research, but it's quite important that also some other researchers consider, okay, we have deep learning, now what will be the next Turing Prize? It will not be deep learning. It will be necessarily something completely different. So think outside the box and how to build models, learn models with other approach than this one. And the field is totally open.
I see. Are there comments? Okay. Any question in the audience? Yeah, please.
To take a very opposite position.
Sure. It's important.
I'm no expert of IA, and I am replacing today my collaborator Stéphane Cani, which is well known in France on the subject. He is very deeply involved in deep learning, as you may know. You know him, and we are also discussing a lot with Isabelle and Renaud about huge models, which is exactly the opposite question, and which is also true. I think both are true. I agree with what you said, and I also imagine that let's say deep learning will go a step further, or several steps further in the complexity, in the complication, in the difficulty, with this big, huge model on which, for instance, a lot of people are dealing, what we call TALN, which is language treatment, etc., etc. So obviously, we have to think out of the box in many different directions, I would say.
Great, thank you.
So I wanted to make a comment.
Yeah, please.
Yeah. So I find the discussion very interesting, and excuse me for the self-promotion, but we just published a little blog post where we go over some of the work we are doing in Leuven, and it's exactly the question of what are the AI models we put on extreme edge devices. So we are not using deep learning, but we are going for probabilistic graphical models, which are much more compact. It touches upon questions of the compiler, because those are irregular graphs that we're dealing with, so we can't have a regular architecture to map any neural network on it. We are dealing with different data types, so that we're not having 64-bit floats, but we are using POSIT representations. So it's actually a nice example that incorporates almost all the aspects that were mentioned. So what I want to say is that I think there is already interesting work going on, exactly covering all these aspects, and yeah.
May I ask which open source platform you use, if you use any for those applications?
I mean, I don't know exactly what open source platform you mean, but it's all. I wasn't part of the research team that built this, but I mean, it's research. They have developed these tools, right? Yeah. No, it's research. Yeah, sorry.
Because we had this whole debate in France about open source platforms that would be European. And there are many, and so yeah.
Okay, no, that was foundational research. Yes.
Okay, thank you. If we go to the methodology of design, so making nowadays hardware software co-design, it means take a lot of decisions, a lot of choices. And so I had always the feeling that the domain of choice of search is so complex that most of the time it's quite an art to design a nice application with both components, making the good choice, the good mapping. So do you have the feeling that we are converging to a methodology which is common, which is structured, which is less artistic and more formal? What is your feeling with respect to the existing methodology nowadays for doing co-design and the state of the art? What is your feeling? Are you happy or what exists, or where do you think people should improve more? I see you smiling. I don't know which.
I don't. Actually, I think we are very far from.
And why? So why do you think we are far?
Because I mean it's very recent. I mean all this area, and we need to combine so many different expertise. That's it's.
So it's still a lot of. Human insight in the design.
Yeah, if I look at what I mean, my expertise, which is compiler, I mean, all this requires us to really rethink the compiler design itself. So it's a lot of work. Whenever there is a new architecture that is coming, you need to redesign. You need, I mean, all those the portability. That was mentioned before is really it's what we call the performance portability. So basically, you need to be versatile to all those new architectures and new algorithms and so it's I think the big challenge, because we do need to have an end-to-end. We need to have some feedback. But it's not just only let's try this solution, let's compile it, so let's execute it and come back, because this is going to cost too much in energy and in time. So we need some shortcuts, and it's really a big challenge.
Yeah, I think I completely agree. I think right now it's a lot of trial and error. There's a famous paper, the Latré paper, which really says that it's right now finding the right combination of a software architecture and a hardware architecture. It's basically the same chance of having a lottery. And the problem is that the timescales are completely different if you want to build a completely new chip architecture. That takes time, takes a lot of time. And if you then link that to the software, it's a completely mismatch in terms of time, and it's also a completely mismatch often in terms of just understanding each other, because these are two fundamentally different principles. Okay, it's engineering, computer science, but still it's hard to really to understand each other. On the other hand, where I think there is a lot of potential, for me, if you look at it from a very abstract way, machine learning is one of the most deterministic programs in the world, in the sense that you know what type of piece of data that you're going to push towards your compute next if you have a certain software architecture. So it's much more deterministic, it's much more predictable than what you would have in a very interactive application where everything can happen. So the data is completely different, but the type of data that you pull is often very much the same.
Yes, I think there is some contradictions inside machine learning AI and general deep learning AI, because the algorithms is quite simple. It's not a complex program. When we consider complex programs, it's much more complex than the algorithms, and in particular after learning for the inference phase. But what is difficult is that the research, there is innovations and progress in research and technical on the algorithms each year. And on the side of architecture, technology, hardware, there is progress also, and variations and proposals, perhaps not each year, but quite soon. But the technology, before to be ready to be used, needs 10 years of work and of development. So we have a real problem of time scaling, and co-design, efficient co-design can be done with stable technologies somewhere. And so we are there. So we have to be very agile, to anticipate what will be needed, and to prepare solutions that will be adaptable, but we don't know how, on which parameter, for the next generation of hardware. And it's quite a challenge, but this needs that the teams has both competencies on algorithms, compilations, and architecture and technology. It's at least 3 competencies different.
I wanted to add an element here. So at my time, at least when I was working on this topic, there was a lot of discussion about performance models, about simulators, so about the fact that data science itself can help the design process. Because when you're talking about trial and error, it means that you can in any way collect a lot of data from simulators, from previous experience. So do you have the feeling that, so this is something we were doing, I was doing at the time 20 years ago. So you say, okay, Codesign is recent, but it's a lot of time that people are working, reasoning about this kind of issues. So I wanted to have your opinion about if data science as a fact of making the process more statistically controlled and taking advantage of data of simulators, so if this can help the entire process. Since at the end we are talking about optimization, so it means we are talking about measures, modeling, complex systems. Please.
So I'm very far from, let's say, basic expertise and experience, but not from my interest. And I will quote again my colleague Stefan, who came to me and very surprisingly to me said to me, you know, IA will help the design of IA chips.
Indeed, what I wanted
so
to claim,
I thought it was science fiction I was doing, but you say you were doing it for 20 years now, and I'm pretty sure it is a very complex and difficult field, but maybe the solution is in the difficulty itself.
Yeah, I agree completely with this remark.
To help the design of a chip, you need the data. And if you never has done the design, you have no data. So before AI will be efficient on designing new chips, you need to have a lot of experience of designing new chips. So it's an open question.
But yeah, completely true. And maybe I'm not sure. Again, I'm far from my expertise, but you will contradict if I'm wrong. What I understand in the full spectrum of valorization I was talking at the beginning, I understand the most difficult will be the CAD tools. And by the way, worldwide, there are only American tools available, Cadence, Synopsys, etc. And it is both a difficulty and a challenge and maybe an opportunity, because there we are talking about new ways to deal with CAD tools. So maybe it will be also an opportunity to recover, to catch up. I don't know if you answer this question. This is more a question.
No, I think it's absolutely correct, and I think we're seeing that those simulation tools, you need to call them digital twins now, or you're out of fashion, but it's basically for a large part the same thing. Those digital twins, and the combination of generating data out of a simulation, but then also transferring this into the real environment. It's an open research challenge, but it's going to be one that is going to transform a lot of or introduce a lot of new applications in that sphere as well. Absolutely.
Yes, so sorry. Okay, I think we are going outside AI scope, but what you said, I think, is very, very important. If you want to have strategic autonomy, we need to consider to be autonomous on the tools we need to use to build the system, to build the AI, to build the software. And it's really critical to ensure that Europe built its own tools. And as these tools require a lot of investment, and we have very nice US or Asian tools for this, we have to consider an original approach. I think an opportunity would be to consider an original approach to build tools by federating several actors around the open source platforms in order to be able to push another way to design the chips, to design the software, to build the AI, and so on. I think it's a real challenge, and it's a challenge that is not well identified at the European levels, because they consider the chips, they consider the research on AI, but very few the tooling we need between them.
Fabrice, the comment, and then the lady in the audience, please.
I mean, maybe I want to just conclude on that. It's more important than what I wanted to say. Still, yeah, I mean, we can discuss afterward, but maybe open source is not enough, but that's another discussion.
Open source, not Totally open. Please.
You talked about the trade-off between efficiency and computational and accuracy, etc. But what about trust? Do you incorporate trust in that trade-off? And what are the main challenges on that? Yeah, I know it's a big question.
Okay, so you have 1 minute. Just
1 minute, it's okay.
Yeah.
Yes, there is as often when we want to optimize, we have to optimize in several dimensions, and one dimension is in contradiction with the others. So probably putting in the design elements that ensures more trust could decrease the performances or the accuracy. And perhaps sometimes if we want a strong trust, so a model simple on which we can demonstrate some properties, we will decide to have a less performance. But it's an open subject because we don't have the solutions ready on the table for trust. We are building the tools and the methodology. And one key element is first to define what is trust. What are the properties? And it's a quite difficult question.
Mm-hmm. I understand, but there is interest from business, from research to incorporate those aspects.
Sure.
Is that right?
Sure,
okay.
sure.
I didn't mention it, but in the second generation of IA, huge project in France, we have four pillars, and one is trustworthy. Mm-hmm. Yeah, of course.
Thank you.
Okay, you want to say something? No. Okay, so just to finish, thanks to all the speakers. So I think you realize that making nowadays an AI application means to make a big journey in complexity, in complex systems at different levels, where different criteria, and the more we reason about that, the more there are criteria which should be considered, like ethics, so energy, and so don't forget this multi-dimensional nature of the problem. So I will stop here, I guess. Okay, thank you all the speakers.